Hello, my name is Russell Richie, and this is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. This is joint work with Ada Aka and Sadi Bhatia. So Preassociation is a task where subjects are asked to generate one or more words in response to a cue word. For example, given the cue mother, a subject might respond with semantically related words like kind, woman, care, in that order, or given the cue star, subjects might respond with moon, sun, sky. And free association is a very complex task. There are thousands of semantically rich cues and responses, and it displays various subtle phenomena like association asymmetries. For example, the probability of responding to stork with baby is much higher than the probability of responding to baby with stork. And in continued responding, at least, as in the examples I gave above, where a subject provides multiple responses to a cue, you can find response chaining, where later responses seem to depend on earlier responses. For example, if a subject's first response to star is moon, they're more likely to continue with sun than if their first response wasn't moon. So perhaps unsurprisingly, given these sorts of challenges and complexities, there haven't been that many cognitive models of free association that have both rich representations of the thousands of possible cues and responses and retrieval processes operating on those representations that give rise to these kinds of subtle response dynamics. So our proposal for cognitive modeling of free association is to combine distributed semantic representations with a variant of the context maintenance and retrieval model. So CMR is, of course, a computational cognitive model that was developed for list recall, where subjects study a list of words and then attempt to recall all of the words one by one. And the basic idea behind CMR is that recalling a word retrieves the context of its encoding, which cues further recall. So CMR basically has a network structure like this, a layer for words that can be recalled and a layer for context. And there's a weight matrix MWC that controls how recalled words activate context, and in turn a weight matrix MCW that controls how context activates words for recall. And then the context layer additionally connects to itself and decays at rate delta so that context persists somewhat as words are recalled. When CMR is fit to free recall data, MCW is standardly initialized with semantic representations from DSMs like LSA or Word2Vec to capture pre-experimental semantic knowledge, and then both weight matrices are updated during list study through Hebbian recall or Hebbian learning. And then with this sort of architecture and training regimen, CMR accounts for a number of phenomena in list recall. Most relevant for free association, it accounts for semantic clustering due to MCW's initialization with DSMs. It accounts for asymmetries in recall since, in general, the two weight matrices MWC and MCW need not be equal to one another. And it accounts for long-distance dependencies in recall because context persists somewhat from trial to trial. Of course, all of these phenomena are known to be at play in free association, or are thought to be at play in free association, so some version of CMR could be useful there. So our primary change to CMR is to add a persistent effect of the cue on context. And we do this because in free association, subjects are plausibly responding primarily to the cue, whereas in list recall, subjects are mostly responding to the most recently recalled words. In some versions of our modified CMR, we also add non-zero biases to the word layer, which conventional CMR does not have, to account for the fact that, for example, more frequent words are generally more likely to be recalled. And so in our modified CMR for free association, the representation for the cue and the decayed representation of previous responses linearly combine into the context layer C with the particular contribution of each of those controlled by gamma. The context layer multiplies with MCW and possibly adds with response word biases to activate potential responses, which are then softmaxed to get response probabilities. And then sieve recall is just a linear combination of the input generated by the word just recalled and sieve recall at the previous time step. We also assume that in addition to having a persistent effect through CQ, the Q is also the first implicitly recalled word at the word layer, so that at the beginning of a trial, it influences C recall, but then its influence decays with subsequent responses subject to delta. So then note that if gamma is 0, then the model just reduces back to the more conventional version of CMR presented in the last slide, where the Q only has an effect at the beginning of recall through C recall. But if gamma, on the other hand, is 1, then we have no memory of previous responses, and every response is just driven by the Q. And we'll get no sort of response chaining or anything like that. So as I said before, when CMR is fit to list recall data, the weights for MCW are initialized with DSMs, and then Hebbian learning further updates these, as well as the weights in MWC. But of course, in free association, there isn't a single word list that is being studied and recalled, and instead the associations come from all of a subject's previous knowledge of the words. So we use DSMs, and particularly glove vectors, to initialize both weight matrices, as well as to get Q representations. And similarly, we use corpus estimates of word frequency from subtlex to initialize biases on the word layer. Now in CMR, MCW and MWC are in general not equal to one another, which allows CMR to produce asymmetries in list recall, but initializing these two matrices with the same glove vectors guarantees that, of course, they'll be equal, which may reduce our ability to model asymmetries in free association. It's also possible that the word frequencies from subtlex corpus aren't necessarily the best biases in free association. So to solve these issues, we can further train or fine-tune MCW and or WB on actual free association data. And then that leads to 4 variants, one in which we train both MCW and WB, 2 variants in which we train exactly one of those parameters, and then a variant in which we train neither of them. And it's also the case, possibly, that fine-tuning these parameters might help make quantitative predictions of response probabilities and other metrics of free association data, improve those sorts of quantitative predictions, in addition to helping account for asymmetries in association. So to train and test these variants, we use free association data from the English Small World of Words project. This is a massive data set of free association with over 12,000 Qs, 100 trials per Q, and 3 million unique responses. To keep things tractable, we only train and test, train on 100,000 trials and test on 10,000 trials, and we keep the Qs in these 2 sets disjoint so that test trials are truly out of sample. Besides its massive scale, a notable aspect of SWOW is that it asks subjects to give multiple responses to a single Q, which often gives rise to this sort of response chaining that I talked about earlier. So there are 2 settings in which we train and test the 4 variants that I mentioned before. In the first, we only train and test on the first responses in every trial. So that's the first responses only setting. And then in the second setting, the continued responding setting, we train and test on all responses in a trial, which entails converting each trial with 3 responses into 3 separate observations like so. And with the data then structured in this way, we can let the sort of recurrent dynamics of our CMR variant play out. In either setting, the recall dynamics of our model are such that for every trial or response time point within a trial, we can easily compute the context representation and then essentially regress the response words onto the context representation, which enables us to fit MCW and WB, the biases, with stochastic gradient descent. In the case of continued responding model, we don't fit gamma and delta, and instead we grid search for the best values in 0, 0.1, 0.2, all the way up to 1. Okay, so here I'm showing the performance for all 4 CMR variants for just the first response setting on several evaluation metrics. So first we see that the full model, the one that trains both MCW and WB, outperforms the less flexible models on negative log likelihood on the test set, and also in predicting asymmetry ratio, which is the probability of a response given a Q divided by the probability of the Q given the response. The full model is also at least as good as the other two flexible models and much better than the no training model by median rank of true associates in model predictions. So for example, the true response to a given Q tends to be ranked about fifth in the full model's top responses to that same Q. On the other hand, the slightly more constrained model, which only trained MCW and had no response word biases, may slightly outperform the full model in predicting empirical response probabilities. And then finally, we also tested all four model variants in their ability to predict list recall behavior in the peers dataset, which is a very large data set of list recall. Here, the model that only trained MCW also seems to outperform the full model in predicting each recalled word given only the previously recalled word. Okay, the continued responding results. So the full model with flexible MCW and WB also outperforms the less flexible models in the continued responding setting. Here I'm showing the values of gamma and delta that gave each model variant the best performance in the training set. And then here is the test set negative log likelihood for each of the four variants with their best gamma and delta. Again, the full model does best. It's also the case that the full model with flexible gamma and delta outperforms the full model with gamma or delta constrained at 0 or 1 by likelihood ratio tests, suggesting that continued free association is best described with a combination of a persistent effect of the Q and partially decaying memory for previous responses. Last, we evaluated our full model's ability to predict response chaining in continued free association. To do this, we calculated the empirical relative log likelihood of every attested Q R1 R2 triplet, which is the frequency of R2 given the presence of the Q in R1 divided by the frequency of R2 given the presence of the Q and absence of R1. For example, the triplet sibling sister brother has a very high empirical relative likelihood because subjects responded more frequently with brother if sibling sister were the Q in first response compared to when sibling was the Q but sister was not the first response. We also then calculated each triplet's predicted relative likelihood according to the full model with flexible weights and biases. The bar plot here then shows the distribution of model predicted relative likelihoods for 5 bins of empirical relative likelihood. And as we expected, the predictive relative likelihoods increase as the empirical relative likelihoods increase, consistent with a response chaining effect in the full model. So to conclude, we find, excuse me, to conclude, we find that a modified version of the context maintenance and retrieval model improves quantitative predictions of free association and list recall and accounts for asymmetry and response chaining in free association. What we're working on now is seeing which of the 4 model variants accommodate effects of, for example, concreteness or age of acquisition, which are known to influence empirical response probabilities in free association. And we're also working on seeing whether our models capture response asymmetries that might be driven by collocation asymmetries in text like cottage cheese. What we're most excited about, though, is that we think and hope our work can go some distance towards providing a framework that unifies modeling of related memory tasks like free association, list recall, and perhaps others as well. Thank you very much.